general relativity, step by step. I've been gradually moulding the Einstein geometrical view of motion into a form where I can compare it with the Newtonian mechanical view of physics in the weak field limit. And we've got Newton's law of gravitation here, so what I want to do is to come out with a tensor equivalent or a tensor approximation to the Laplacian of the gravitational potential energy phi. That's gravitational potential energy, hot energy, as a function of position in the steady field. Okay, well that equals eta, and I might change the variables ij di to phi by di x I di xj. Both left and right hand sides are scalars. The right hand side is scalar because we're summing over I and j. Okay, well what does that equal? Well, by looking at this formula here, for the Riemann-Christoffel tensor with 2 zero indices there, I can show, well, it's obvious, that that's equal to R. Let's get this right. We're summing over the top and the bottom, and we are using the fact that the metric tensor is diagonal to give myself an alpha 0, alpha 0. Now I'm getting somewhere. I've got a very classical thing here. This is the Laplacian of the gravitational field potential energy, and on the right hand side I've got something that's in terms of the Riemann-Christoffel tensor. Now I can use the fact that R alpha beta gamma, well, let's stick to the standard notation that I've been using, R alpha beta mu nu equals minus R alpha beta nu mu. So you can see that it's anti-symmetric in these two terms here. So what that tells me is that R 0 0 0 0 equals minus R 0 0 0 0, so they both must equal 0. So I can re-express this thing here as R, instead of alpha, I can just put a Roman index I 0 I 0. Of course this is summed over I, and we've got a contraction of the Riemann-Christoffel tensor on the first and third index, which is the 0 0 component, the 0 0 component of the Ricci tensor. Right, well that's good. So now we've finally established that the Laplacian of the gravitational potential is equal to the 0 0 component of the Ricci tensor. And you'll remember, not last screencast but the one before, I think it was, I spent a great deal of time, see if I can find it, putting the Ricci tensor on the left hand, here it is, putting the Ricci tensor on the left hand side of the gravitational field equations. So now I can use that to try and pin down this value of k here, which has been uncertain for quite a long time now. So I'll do that on the next screencast, and I'll stop here just a minute. Let me just summarize what I've done. We've got this. This is a weak field, slow moving, stationary potential approximation. And the field equations had better work in this circumstance too. It had better work, so that will allow me to pin down that factor of k. I'm going to stop there. Stop.